Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Satisfaction problems, so some of this will be repetitive to a few of you. We'll start off with some very basics, even more basic than that, random k-sat and what sharp thresholds are. So random k-sat, I mean, just in case there's one or two people here who don't know this, you take n variables and you pick m random k clauses, and the interesting range is where m is a constant times n. And each such collection is equally likely, and you're concerned with the probability of satisfiability. And so, for example, suppose you're doing 2-sat. When C is small, like a half or so, your probability of satisfiability is very high. It's essentially 1 minus a little over 1. And then as soon as it bumps from just 1 minus epsilon to 1 plus epsilon, it drops from 1 all the way down to 0, asymptotically. And 3-sat does a very similar thing, with a subtle difference being, well, first of all, we don't know the exact number where it drops, and second of all, we don't know that there is an actual number, but something very close to this happens. I won't go into that because that's a 5-minute talk all by itself, but something very close to this happens. That was due to Friedgut. 3-colorability of a random graph, a very similar thing happens, just like random 3-sat, it drops suddenly. And those 3 pictures, we call them sharp thresholds of satisfiability because, like I say, you start off, you're with high probability you're satisfiable, then all of a sudden you drop to high probability unsatisfiable, or non-3-colorable. And 2-colorability I put up as an example of what we call a coarse threshold, which basically means not sharp. You see what's happening here is instead of dropping suddenly from 0, or from 1 all the way to 0, there's sort of a gradual drift. Okay? And by the time you get up to 1/2 times n edges, then it's 0 probability, or asymptotically 0 probability that you're 2-colorable. But before that, we got a slow drift. And so what I'm interested in this talk is in general, when we look at different types of problems, in which cases do we get this sudden drop, this sharp threshold, and in which cases do we get a more gradual drop, a coarse threshold?
Do you distinguish at all if there is no point where it's 0? So this you call still a threshold, or what do you call it?
You mean if it just starts at 0 right from the start?
No, what if it goes from 1 to 0, but there's no threshold like 1? You have to go to infinity before you get to 0.
Basically, it never goes to 0 in finite, for finite values of the formula.
Yeah, so more generally, I mean, there are problems where the correct scaling parameter is not order n. And so you maybe want to do n time, c times n root n or something at random edges. And usually,
but if you look at the birthday paradox or so, if you do the right scaling, the one set is the right scaling and it's a curve.
Right.
But it never goes to 0 unless you go out to infinity.
Oh, I see what you're saying. It just, yeah. Okay. Yeah, I guess I'd call that a sharp or a coarse threshold as well. And, yeah. But okay. Now, in the family of problems that I'm going to be focusing on, that never happens. And in fact, in that family, the correct parameterization is always c times n. So, the main tool we want to use when we're studying sharp thresholds is Friedgut's theorem. Basically what happened is, for some time, there were a lot of individual problems that people could determine the threshold of, that they were sharp and so on. For example, 2-sat was known to have a threshold of 1 for a long time. And then Friedgut came up with this technique which often establishes a sharp threshold without necessarily telling you where it is. And his theorem is what was used for each of these 2 pictures, 3-sat and 3-colorability. And I mean, his theorem says something much broader than what I'm saying, so I'm restricting it to generalizations of 2-sat and so on. things where the scaling, where the correct parameterization is order n edges, order n clauses. If the threshold is coarse, then for some C, meaning a C in the range where you're drifting between 1 and 0, you can come up with a unicyclic graph or a formula, H, such that conditioning on the appearance of H boosts the probability of some epsilon. Okay? As a constant size unicyclic, actually. And so it's best illustrated with two-colorability. Essentially, two-colorability, you're two-colorable if and only if you don't have any odd cycles. So if you condition on the presence of an odd cycle, say a triangle, then you're going to boost the probability of not being two-colorable by a lot. You're going to boost it all the way up to 1 in this case. Okay? Not always do you boost it all the way up to 1. Sometimes you just boost it by the epsilon, but, or at least with one particular H. But what Friedgut showed is that in some sense, anytime it's coarse, it's a generalization of two-colorability in the sense that you can take a particular unicyclic graph or formula, Boolean formula, and conditioning on that graph being there, Boolean formula being there, you bump the probability of unsatisfiability, non-colorability, what have you. Yes. And the idea is that in this range, if you name a unicyclic H, there's sort of it's neither almost surely present nor almost surely not present. There's kind of a epsilon 1 minus epsilon chance of H actually being present. And so the curve that you see, the probability that somewhere between 0 and 1 of satisfiability is somehow related to the probability of H being present. So intuitively, that's why we get coarse thresholds out of this. And it's sort of a one-way direction is easy to show. If you get a constant size unicyclic H that is unsatisfiable, okay, sort of like the two-colorability case, then you definitely get a coarse threshold. And there's some trivial exceptions. The trivial exceptions would be if, like, you're almost really unsatisfiable right from the beginning. But I'll sort of ignore those for now. But basically, the idea is if you get a unicyclic subgraph or subformula that's unsatisfiable, then there's a chance that it'll be there. There's a chance that it'll appear. And then the probability of unsatisfiability will have something to do with the probability of this appearing. And Friedgut's theorem almost says if and only if here, but not quite. Okay? Friedgut's theorem says you don't necessarily need H itself to be unsatisfiable, but you need H to kind of boost the probability of unsatisfiability. So if you get a subgraph H that's not necessarily unsatisfiable, but its presence sort of boosts the probability of the entire formula being unsatisfiable, you also might get a coarse threshold. Now, in most of the early examples of proving things were coarse thresholds, a lot of the early coarse thresholds that we came across sort of only came across for this reason, that you had a unicyclic H that is unsatisfiable. Okay? The cases where there is no such H, but yet there are the H's that kind of boost unsatisfiability are a little bit more rare. We'll see a couple of examples of those today. Now, so I said I'm going to talk about a bunch of models that kind of generalize k-sat and so on. So here's an example. Here's examples of some. So I just sort of threw a few arbitrarily up there. You want to generalize k-sat. So, I mean, one direction a lot of people went in studying generalizations of random k-sat, or they look at all the sort of things that you get from, Schaeffer's dichotomy theorem, the sort of family of generalizations of SAT. So, for example, 3 XOR SAT is one that's been well studied. Each clause has to have an even number of true literals. That one is known to have a sharp threshold, and in fact, it's known exactly what that threshold is. Dubois and Mandler determined the exact threshold for that one. 1 in k-sat, each clause has to have exactly 1 true literal. That's also known to have a sharp threshold, and the value is known there. That, goodness, Equioptus, I think it's Strati. Sorry, actually. Okay. My memory's waving on exactly what who the four people were that did this. I think Chris Moore was another one. And you can sort of mix things a bit. So you could say, I'm going to throw down C times n clauses, and half of them are going to be k-sat clauses, and the other half are going to be 1 in k-sat clauses. Okay, that would be an example of sort of a mixed problem. Okay, or maybe, you know, a quarter of them will be 1 in k-sat, a quarter 3 XOR sat, and a half k-sat. Okay, so you're mixing up a bunch of different types of clauses. And one theorem is, Gabriel Estradi proved this first, Craignow and Donnet proved something very close to it, very similar, that in all these generalizations, you're going to get a coarse threshold if and only if there's some unsatisfiable unicyclic formula H. So remember we said on the previous slide, if you've got an unsatisfiable unicyclic H, you automatically get a coarse threshold. Friedgut's theorem isn't quite if and only if, because it says maybe you'd get a coarse threshold without the unsatisfiable H, but an H that boosts. And what they proved is in this realm, you can never have an H that just boosts without having an unsatisfiable H. Okay. So there's... No, but I will.
Okay.
Now you call it generalized k-sat, so this includes k-sat.
Yes, this definitely includes k-sat. So basically what I'm saying here is if you're familiar with the Schaeffer's dichotomy theorem in his paper, all these different kinds of constraints that he considers. Oh, good. Yeah. So we'll think of it as a hypergraph. So we've got the variables, and for each clause it's say it's 3 sats, so each clause will be a hyperedge of size 3. So here's what I would think of as a cycle. So by a cycle, I want a sequence of edges such that you can think of the endpoints of the hyperedges meet. So each pair intersects in exactly one edge, or exactly one vertex, and then maybe we'll add a sort of a tree-looking thing coming off of it. Okay.
So if say the middle point of that edge on the top is also the middle point of the edge on the bottom, that you would not.
I'm not counting that. And yes, I should have been more. You're right. Definition of cycle on a hypergraph is hard to see. I should specify that. And the idea is that these are the structures that can show up when you've got a linear number of edges in your random hypergraph. And when you've got a unicyclic, when you name some unicyclic thing that actually has one cycle, the distribution of this object and copies of this object is sort of a Poisson distribution in your random formula with a linear number of edges. And if you name any type, anything, name, for example, this one, and pick a random free uniform hypergraph with a linear number of edges, there's sort of a, well, it's not 50-50, maybe it's 60-40, but something like that chance of whether or not there's at least one copy of this. And if you get such a structure that's unsatisfiable, then there's, that 60-40 chance of whether or not that particular unsatisfiable one shows up. And once you've got that, you get a coarse threshold. Because, well, the probability of satisfiability ends up being tied really closely to the appearance of one of these things, especially in the early parts. Okay? What really happens is, if you've got, if the number of edges is very small, say epsilon times n, so you haven't quite formed a giant component. So one of the standard things with random graphs, random hypergraphs, is a linear number of edges, something dramatic happens when they cross a magic number. So with edges, when you get half and different edges. And before that, you got a bunch of little trees and unicycle components. And after that, you got this big, complicated tangled thing. Okay? And except for the trivial cases, if you've got trees, you can always satisfy. So at the beginning, say, for example, you got this as a unicyclic component. And suppose you're at epsilon n edges. Then there is a decent chance that every component will be a tree and so will be satisfiable. Okay? There's also a decent chance that this one will show up, and so the whole thing will be unsatisfiable. And so because of this, if you've got some unicyclic unsatisfiable thing, then your graph is going to look something like that 2-colorability plot.
I don't understand it. 3 sets, why they would never lead to unsatisfiability. I could always use the middle variables to satisfy everybody.
That's right. So in 3-sat, you can't possibly form one of those, and that's why 3-sat is a sharp threshold. In fact, in 2-sat, you can't possibly form one either. It's not quite as obvious, but it'll take you a minute's worth of thought versus a second. But and so again, so once when we're in this realm for the graphs, and a similar realm happens for 3-sat and k-sat. Way back here is in the range where you've got a decent chance of everything being a tree. You know, maybe a 30% chance of everything being a tree. And so you've got at least a 30% chance of satisfiability. You've also got maybe a 2% chance of that particular H showing up. And so you've got at least a 2% chance of unsat. And therefore your probability of satisfiability is bounded away from 0 and from 1. So having these unicycle graphs forces a coarse threshold that starts drifting down from here. And this theorem says that having those unsatisfiable unicycles is the only thing that can force a coarse threshold. Friedgut says that in general, a coarse threshold can be forced either by an unsatisfiable unicyclic or by a unicyclic that's satisfiable, but its presence sort of boosts the probability of unsatisfiability a bit. And what they show is that the latter case never happens in the generalized sat.
But can I see why this would, for example, not happen in k-sat easily?
Why, later on in the talk, I'll go over that. But it's not trivial. Like it takes a bit of work after this to prove the k-sat. So the first top is this half of the page is going to be a more formal description of that generalized sat. So a clause of size k is a list of permissible truth assignments to the k variables. Okay, so in general k-sat, maybe you get a clause that says A or B or not C. Then there's 7 possible truth assignments we can give to those 3 variables. Okay. In kx or sat, has to be even, I guess, there's 2 to the k minus 1 possible truth assignments that can be given those variables. And for any type of clause you want to consider, you can think of a clause as just a list of possible truth assignments. Okay. And so we take order n ordered k-tuples of those variables to form our random problem. Okay, so first you pick the sets of the k-sets that are going to form your random clauses. And then you have to say exactly what kind of clause that's going to be. And so somehow you, at random for each of those clauses, pick what the list of permissible values is going to be. Okay. So for example, if we're going to do the one where I said half of them are kx or sat clauses, half of them are k-sat clauses, your distribution here would be a flip a coin with 50% chance it's k-sat, 50% it's 3x or sat. Okay. And in fact, it's a little more random than that because even with k-sat, it seems like every clause is the same, but actually there's a random choice there because it's a random signing of the variables. So with 3-sat, there's actually 8 possible constraints you can put on, right? 8 possible ways you can sign the variables within that clause. So with 3-sat, you're listing, you know, all the possible sets, the 8 possible sets where you permit 7 out of 8 assignments. Okay. And each one of them is chosen with probability 1/8. So that's what random 3-sat is. Random kx or sat, I guess it's a 50-50. You're either saying, no, it's not quite that, but again, it's a similar distribution. Okay. So that comes down to essentially the signing.
So you don't require that the constraint is symmetric on that change?
Not necessarily, no. A lot of the common models would require that, but I'm not forcing that. So basically, this is sort of a general way to describe all this wide class of models: random 3x or sat, random 1 and k-sat, random k-sat, et cetera, and going a little bit broader into ones where we mix things. 2 plus p-sat can fit in under this thing, and so on. And under this half, under this broad family, this is what Estradi and Craignow and Daudet proved, that here, if you're coarse, it's got to be because you have a unicyclic age. There can't be anything else forcing coarse threshold. And generalizing it slightly further, we simply expand the set of permissible values for the variables. So everywhere up here, the variables have to either take on true or false. Might as well say have to take on values 1 or 2. And you can generalize a bit further saying, well, let's say they have to take on values 1, 2, or 3. Okay? Or 1, 2, 3, or 4. And your constraint, again, is a list of the possible permissible assignments for the k variables. So for example, if you want to do 3-colorability, okay, we're going to, all the clauses will have size 2, so k equals 2. And, d will equal 3, so every vertex, every variable has to take on one of 3 values, 1, 2, and 3. And the clause is the list of permissible assignments, so it's just, you can give it any pair as long as it's not the same value. So you forbid 1, 1, you forbid 2, 2, you forbid 3, 3, and the other pair of values is permissible. And in this case, P is very simple. We give the exact same constraint to every edge. And these are called constraint satisfaction problems when you extend the range a bit. And this is a broadly studied class of problems in artificial intelligence and so on. So the natural question is, this result of Estradi and Craignow and Daudet, does it generalize for the general constraint satisfaction problems? And the answer is no. So, tell you this and at the same time give you another concrete example of these constraint satisfaction problems. Okay. So for D at least 3, this theorem doesn't hold. So here's an example of a random constraint satisfaction problem. So first of all, it's a concrete example for those of you who didn't quite digest that definition. And second of all, it's an interesting example in that it's one that every unicyclic problem that you can form using these constraints is satisfiable, and yet you get a coarse threshold. So how does this model work? Well, in this case, k equals 2. So a k-uniform hypergraph is just a graph. So we pick a random graph. And on every edge of that graph, we put down one of these 2 constraints. And probability is going to be 2/3 that it's C1, 1/3 that it's C2. Okay. So 2/3 of the edges will look like C1, 1/3 will look like C2. Now C2 is just that 3-colorability constraint I described earlier. So on this random graph, anytime you got an edge that's a C2 edge, we're saying that you can't possibly give those 2 endpoints the same value. And every time you got an edge that's a C1 edge, we're saying if one endpoint is...
So what you're drawing there are the ones
Oh, I'm sorry,
not
yes.
allowed.
Yes, those are the not allowed. I'm using red for not allowed. Yeah, definitely should have said that earlier. So with the C1 edge, what we're saying is if one endpoint gets 1, then the other one has to get 1. And any combination of 2, 3 is fine as well. And the question is, can you assign values 1, 2, and 3 to the various vertices such that all these edges are okay? And it's not hard. It's a simple little exercise to show that if you make a graph that has at most 1 cycle, and you let the adversary put one of those constraints on every edge, it'll always be satisfiable. You'll always be able to win.
Is it clear that there is not a generalization of the ICD theorem which involves something other than a cycle which is more appropriate for D equals 3? I mean, a cycle is kind of a D equals 2 notion, it seems to me. I don't know.
Yeah. No, where the cycle comes from is the fact that the underlying thing is a graph. And if you've got a random graph with a linear number of edges, and you want a fixed subgraph to show up, have any chance of showing up, it has to have at most 1 cycle. Right, so that's actually where the cycle is coming from, not the D equals 2, but from the fact that it's a random graph with a linear number of edges. So this is a much more subtle coarse threshold.
I know that's not true in general, but is this an example of a graph homomorphism?
No, but I'm going to talk about graph homomorphisms in a little while. Well, if you generalize the notion of homomorphism enough, then it is. But the basic homomorphism question, that's not quite what this is. So what's going on? So what's going to happen is there's going to be this range of values where you can think of this as two different graphs, right? You got all the C1 edges and the C2 edges, the two different graphs in the same vertex set. And there's more C1 edges than there are C2 edges. Okay? And the interesting range is going to be when there's so many C1 edges that they form a giant component. But there's not enough C2 edges to form a giant component yet. Okay? So let's say C equals 1 will do the trick, right? Because if you got, so then you'll have 2/3 times n C1 edges, which is more than a half, and 1/3 times n C2 edges, which is less than a half. Okay? Now, what's going on in this giant component of the C1 edges? Well, in the giant component of the C1 edges, if you let any variable in that giant component have value 1, then the entire component has to have value 1. Okay? So you've got this giant component of C1 edges, and everyone in here, if at least one variable has 1, then everyone has to have 1.
I don't understand why this is C1 by itself.
Well, the C1 by itself is. But the union of the two then becomes some sort of generalization of graph homomorphism. Essentially, you have two different target graphs, and some edges have to homomorph onto one and some onto another. So, so the C1 edges form a giant component. And within any component of the C1 graph, in particular the giant component, if some variable gets 1, then everyone has to get 1. And it's not hard to... And so now you pick your C2 edges, and almost surely you're going to get at least a few C2 edges lying in here. Okay? And the C2 edges forbid both endpoints from having 1. And so what happens is almost surely you're just not able to use 1 anywhere in that entire giant component. And so within that entire giant component, you're forced to use 2 and 3 only. And when you use 2 and 3, it reduces it to essentially to 2-colorability. Okay? So you have to 2-color the giant component. And so now you get a coarse threshold. Okay? So it's a much more subtle coarse threshold jumping out. Essentially, we force it all down to 2-colorability. But in doing so, you need this big global thing going on with the giant component. So you can't find a single unicyclic graph that's all by itself unsatisfiable. Yes?
So the unicyclic graph that boosts the probability of unsatisfiability is the triangle of C2.
Exactly. So you take any odd cycle of C2, and if there is such an odd cycle, then conditional on there being that triangle, there's at least some epsilon chance that the entire triangle lands inside this giant component. And so that boosts the probability of unsatisfiability. And there's a chance that there's going to be no triangles. There's a chance there'll be no odd cycles because the number of C2 edges are before the giant component. And so there is a chance that we'll be able to just satisfy everything using 2 and 3 only. So, so there's a coarse threshold. So here's my overall goal, which I think is overambitious. It certainly is. I have to weaken the goal somehow. But roughly, I want to characterize which models have these sharp thresholds. And really what I want to do is I want to learn in what ways can you get a coarse threshold forced by something other than unicyclic H. And I really want to understand in what ways these coarse thresholds can arise. And, you know, the natural way to understand is to try to characterize when you get coarse versus sharp. And I don't think I'm going to be able to do that, so I'm going to have to come up with some other way of understanding, or maybe just give up on understanding them. But here's an example that says why it's overambitious. In order to decide, so I've got two constraints. Now I've got to tell you what this means. The red thing, again, means I'm forbidding these pairs. And when I put a big red line here, what I'm saying is I'm forbidding any pair which has one value from the top and one value from the bottom. So this edge sort of says if you've got an edge between two variables, they've either all got to be 1, 2, or 3, or they've either both got to be 1, 2, or 3, or they've both got to be 4 or 5. So in both those cases, I'm putting that restriction in. And my claim is that if I want to sort out whether so I'm putting probabilities 0.7, you get C1, 0.3, you get C2. If I want to say in general, for different choices of probabilities here, whether you always have a coarse versus a sharp threshold, I'm going to have to figure out the exact value of the 3 colorability threshold. And that seems like a hard problem. So determining whether just the model that looks like this, uses these 2 constraints, is coarse or sharp, requires figuring out the 3 colorability threshold.
Well, what if you just had a theorem in terms of the 3 colorability threshold?
Yeah, so that,
I mean,
yeah.
Right, that would be a reasonable, like you got like a, basically like a percolation threshold.
Exactly.
One of them, and then based on whatever that is, you could prove this
Right.
theorem.
So hopefully I would do something like that. But somehow I've got to adjust this thing. And there's a few other nasty examples floating around that.
If you didn't know that the 2 colorability was 1/2, you wouldn't have been able to give us something that would have told us that the last because it wouldn't have said that, you know, by putting probabilities together.
Right. Yeah.
One way above and the other way below.
Yeah, no, you're right. So definitely we might be able to do something like, to get around this example anyway, say in terms of 3 colorability threshold.
Right.
But, I mean, there's more subtle other ones that come up too. So, I mean, there's more reasons for this that I'm not optimistic about getting this entire goal down. But I'll show you why this requires 3 colorability threshold.
Here is side of it. But I mean, okay, maybe it's the wrong notion here, but I mean, Jennifer said, well, what if I now combine many different thresholds, right? There's a number of thresholds that would combine and go up exponentially with the size of the system.
So something that's not clear, actually, so we might get one of these situations where, sort of like Friedgut allows, there's a possibility that maybe the 3-sat threshold sort of fluctuates a little bit. Using this example, if the 3-sat fluctuates a bit, you can create something where, you know, for some values of n you got sharp, and for other values you got coarse. And so that's a little strange, and that comes towards, says something along the lines of your decidability question, I think. So what's going on here? So again, let's picture blue edges and green edges. And within any one component, you got to commit to either using values 1, 2, and 3, or values 1 and 2. Okay? So let's pretend for a moment you got to do that for the whole graph. That's not quite what's going on, but I think it's easier to see that way. So you've got 2 graphs, okay, the C1 graph and the C2 graph, both in the same vertex set. Okay? And you've got to assign values of the you've got to either assign the vertices all either 1, 2, and 3, or you got to assign all vertices either 4 and 5. Okay, so you got to either use the top 3 colors or the bottom 2 colors throughout the graph. Okay? Really, the rule isn't throughout the graph. The rule is one component at a time. But let's do throughout the graph. Okay? And your assignment has to be such that.
I do want to take my questions here. Is it
Okay.
decided? Could I make a Turing machine which holds if the model has a sharp threshold?
I don't know. I haven't pondered it, and I'm not optimistic that I pondered it for 2 minutes. I'd be able to give you a good answer. It's definitely worth thinking about afterwards. So, and the rule is at the end you must have either 2-colored the green graph or 3-colored the blue graph, one or the other. So, if you look at this plot and you look at the probability of being able to do the task of 2-coloring the blue graph, or the green graph, I mean. Actually, let's use green for green graph. It sort of drifts down, and hit 0 right at the point where the number of green edges is 1/2. So what's that? What do you have to be 30% of to be 1/2? 3 times 5/3 maybe? Okay. 3 times 5/3 is 1/2, I think. Good. So by the time you get to 5/3, there's no chance of succeeding by 2 coloring the entire graph. Before that, there's a chance of succeeding by 2 coloring the whole graph. And then you ask, what's the chance of succeeding by 3 coloring the blue graph? Okay. Well, it's a sharp threshold, so it's going to look something like this. Maybe it drops suddenly there. Okay. And if it drops suddenly there, then the overall probability of succeeding is going to look like this. Up to here, you almost surely win. I won't bother trying to 2 color because there's a chance of losing there. I'll be able to 3 color. And then right here, I got a drop. And at this point on, I've got to give up on 3 coloring. Okay? So I better be trying to 2 color, and I've got a chance of winning. So I drift down. So I get this little coarse region. Okay? But that's if this 3 colorable drop happens here. If instead the 3 colorable drop happens over here, okay, then my probability of success looks like this. At all points, I might as well just try to 3 color. Probability of 3 coloring is at least as high as 2 coloring in that range. And so figuring out whether I've got a coarse or sharp threshold means I've got to figure out exactly where this line drops. And that, of course, depends on where the 3 colorability threshold is. I picked 0.7 and 0.3 because right at this point, where we've got right at c equals 5/3, the number of blue edges is what? Oh, I'm off by a factor of 2. Okay, I should have picked other numbers. Anyway, if you pick the right numbers, I think I'm off by a factor where I know what the answer is in this case. I end up picking this to work out to 1. Anyway, it doesn't matter why I did that. But you can see that for whatever values, for whatever however unsure I am about where the 3 colorability threshold is, I can pick appropriate numbers here and here that I won't, that the threshold might be here or here. Okay? So that's why clearing up this particular image seems to be hard, unless you do something like saying, in terms of the 3 colorability threshold. So, all right, so what do I do? What do we do? We can't figure out, can't solve the whole problem. So what we're trying to do is zero in on some sub-problems that might shed some light or maybe restrict our attention to certain subfamilies of these generalized SAT. So here's, I'll mention a couple of subfamilies that we do know how to deal with. Okay. And this is joint work with my master's student, Hamid Hatami. So there's this DKT model that's commonly studied, because it's a fairly natural way to generate these. Okay. If you're one of these people, if you still don't quite have an idea of what that general model was, is a odd distribution about putting the constraints in and so on, at this point you don't have to know it anymore. We're going to talk about a couple of much simpler models. Okay? And these are sub-cases of that general model. So don't worry about the general model anymore. Here's a sub-case. Constraint size K, domain size D, and each constraint forbids exactly T k-tuples. So what's going on is every variable has to take a value from 1 to D. Okay? You want to throw down some random constraints. So you pick a bunch of K sets of the variables. Those are going to be the sets that get constrained. And on each K set, you pick exactly T k-tuples of values. And you say you're not allowed to have those T k-tuples. So that's the whole problem. And for example, domain size 2 t equals 1, you get k-sat. So this is a nice way to generalize k-sat. Right? So you've got d equals 2, so you're really doing truth assignments. Let's say k equals 3. So you pick a bunch of 3 sets of variables, and on each 3 set, you pick exactly one truth assignment that they're not allowed to have. Well, that's exactly a 3-set clause. And for this particular model, we can prove that you get that thing, coarse threshold, if and only if an unsatisfiable unicyclic H. Okay, so you don't have the subtle coarse thresholds on this model. I'll say a bit later, perhaps, about the proof of that.
Those forbidden CK-couples are chosen again from the geometry?
Yes, yes. So you take all the, d to the k, choose d, or I guess d to the k possible k-tuples. D to the k choose t sets, and each set is equally likely. And the second one, to Christian's great interest, is graph homomorphism. So, first of all, I think there's a natural question just from a graph theoretical perspective, but it actually springs out, even if the notion of homomorphism had never been looked at before. This springs out as a natural subclass of the family I just described in the following sense. Suppose you're restricting attention to the k equals 2 case. And suppose you just don't like the fact that I'm allowing you to mix all these different kinds of constraints. So this is a model where you're going to say, I want you to just pick one constraint and put the same constraint on every edge. So k-colourability, for example, is an example of that. Okay. And if you make that rule, you've got to pick the same constraint, put it on every edge, you get exactly graph homomorphism. Now we've got to be a bit careful about what it means, same constraint on every edge. Let's say k equals 2, d equals 3. Let's say these are my permissible values. Okay? Well, there's a couple things wrong with this. One thing that's wrong is it's not symmetric. And if I want to put the same constraint on every edge, well, it matters here which way it's directed. So I better make it symmetric if I'm going to allow the same thing on every edge. So I'll do that. And there's another problem here, is I'm permitting the pair 1, 1. And so I put that constraint on every edge, I'll just assign every vertex value 1, and the whole thing's trivially satisfiable. So I better not permit anything like that. And once you say that that's what your constraint has to look like, what you've got is a loopless graph homomorphism problem. And we have to insist on it being connected. Some awkward things happen with the disconnected case that are similar to what happened with that 3-colourability threshold type example I put up a couple of slides ago. I won't go into those. But as long as it's connected and loopless, then we again get it's a coarse threshold if and only if you have an unsatisfiable unicyclic H. And it turns out with homomorphisms are well studied. If you've got an unsatisfiable unicyclic H, it's got to be because T is triangle free. So if your target graph you're trying to do homomorphism to has no triangles, then it's not hard to see that you can't get a homomorphism of the triangle to it. So the triangle becomes an unsatisfiable unicycle. Okay? And it turns out that that's essentially the only kind of unsatisfiable unicycle that you can go. In other words, if any unicycle doesn't have a homomorphism, then the triangle won't have a homomorphism. And
now your general constraint, let's say in the d equals 2 case, is not quite that you choose a different graph a different target graph for each edge because of the asymmetry.
That's right. So I guess the general thing is, first of all, we allow the direction for the edges, and then second of all, it's a different target graph for each edge. And so essentially, it's directed graph homomorphism with different target digraphs. And directed graph, we tried, and we couldn't make this work out. Now, I should say, what I'm going to do here is I'm going to start talking about the different things we know at this point, we being my student and I. This is sort of we're very early into this project, and but I wanted to talk about it here in hopes of drumming up some interest. Hopefully some people here will have some ideas and will give us something to think about over the next week and a half while I'm still here. So digraph homomorphism is an example. We haven't actually hit a wall or anything on it, but the proof for this just doesn't work. And it's quite possible that 3 hours work with a nice idea will knock it off quite easily. I'd be very happy if someone here provides that nice idea. Okay, so those are two examples of natural classes where it turns out we don't get the interesting thing where you've got a subtle coarse threshold, a coarse threshold not caused by a unicycle. Now, as I said before, the case where the domain size is 2 is well understood. You only get a coarse threshold if you've got an unset unicycle. So we tried to move up a little bit to do d equals 3, and we couldn't get very far. We couldn't get past k equals 2. So, actually, I won't put that up yet. I'm going to put up an old picture. So here's one where k equals 2, clause size 2, domain size 3. And what in studying the general case, the most general case with domain size 3, clause size 2, essentially, if you've got a coarse threshold, either you've got to have an unset unicycle, or something very, very similar to this one has to happen. Okay? So we can say that much. And we don't know how to push that even up to domain size 4 or k equals 3. Maybe with some more thought we can manage to do that, but at this point we can't. But here's what we can say. Remember, the problem with this one was we got this big giant component where if one of the variables in that component gets value 1, then the whole thing has to get value 1. And so basically, and you can't have that. You're going to be unset if you make the whole thing 1. So basically, you've got that whole giant component that can't take 1. And what we can show is that something along those lines has to happen. So it's got to be that if you force one variable to take value 1, then some sort of spreading of the forcing takes place. And setting a variable to have value 1 is going to force a large number of variables to take value 1. So same idea. A substantial number of the variables are going to have the property that if they take value 1, then order n other variables are going to have to take value 1. And then when that happens, well, it means that something's going on like what's going on here. So that is what this means. If there's a coarse threshold and every unicyclic is satisfiable, then it's got to be that there's order n variables, so some delta n variables v. For each one, there's this set fv, so that if you set v equal I, so I equals 1 or 2 would do as well, then for all the vertices in fv, you've got to force them all to equal I. So you've got some big blow up. So we can say that much. So we got a decent understanding about what can cause coarse thresholds in this very restricted case. If we try pushing that to d equals 4, then it doesn't quite work out. So we'll do one of these things. So if I want to generalize this one to d equals 4, to avoid clutter, I changed it a little bit. So first of all, what I did was I took value 1 and kind of blew it up into a double value. So 1 and 2 now become twin values. And the other thing is I changed this C1 constraint to something that just looks like this. Okay? So I put it up the other way before to make it nice and symmetric. Now it's going to be asymmetric, and what it says is x equals 1, then y equals 1. And that obviously also will allow a big forcing thing going on. If you set one guy equals 1, so it's now directed, yeah. So if one endpoint is 1, the other endpoint is 1, and as long as you have enough of those guys, then you get this blow-up thing where if you set one guy to be 1, then it's got a whole bunch of vertices it's got to pass to. And then what I do is I blow up vertex 1, so I get twin values, 1 and 2. And basically what this problem is the same thing as the other one. And so for the very same reasons, this has a coarse threshold. Okay? So what happens here is, instead of saying if we assign its vertex value 1, then a whole bunch have to have value 1, we say if we assign it a member of 1 or 2, then a whole bunch of them have to have 1 or 2. And if we get a lot of these constraints going in, this sort of says you can't have both 1 and 2. And so if you get a few of these going into that big set of vertices that have 1 or 2, then you become unset. And so it ends up being, for the very same reasons, this has a coarse threshold. But I can give you a different problem that also has a coarse threshold for a subtly different reason, what I'm doing is I'm breaking apart those two constraints. Okay. The main thing is this splitting. I broke that constraint up into two parts. Okay. So I used to have a constraint that says if you've got 1 or 2, then the guy I'm pointing to also has to have 1 or 2. Now I've got one constraint that says if I have 1, then y has to be 1 or 2, and a different constraint says if I have 2, then y has to be 1 or 2. Then I split this one up because I wanted to have a lot more of these than this. Okay, so then I got to throw my so when I put my probabilities down, you know, there's going to be like maybe 100 times as many of these as there are of these, or something like that. Probably I don't need 100, but quite a few more. And so what you've got is, so C1 and C2 are different types of edges. I seem to be gradually losing my markers. Oh well, I'll make do with green and black. So I've got a vertex, and you know it's got a few children, and each child might have some green edges and some black edges. Okay. And let's say the green edges correspond to constraint 1, the black correspond to constraint 2. And let's say I've decided I'm giving this one value 1. Okay. Well, that means these two both have to be either 1 or 2. Okay. But I have some choice. And if I make this one value 1, then it puts constraints on these two. If I make it value 2, then it only puts a constraint on this one. So I don't actually have a fixed set of vertices that are going to be forced. This one might be forced, or this one might be forced to be in set 1 or 2, depending on what choice I make here. Okay? So it's a little more subtle. But what one can prove is that as long as the branching number is high enough, as long as we've got sufficient number of these, then setting this to be 1 forces order n values to be either 1 or 2. So setting this to be 1 or 2 forces some set of size order n to be 1 or 2. But it's not a fixed set. You have your choice as to which set it is. But some set's got a size order n has to be 1 or 2. And if you have sufficiently many of these, it's not as obvious why that will produce unsatisfiability, but it will. And so a very subtly different thing happens where, again, you're not forcing one fixed set to have all value 1 or all value 1 or 2. But you're forcing a large number. So it's different than the previous situation. And we can't prove that this is the only thing that happens in this set yet. I mean, or at least we haven't proved it yet. So, anyways, the understanding I gave of the 2-3 case just doesn't extend here. And it doesn't extend to constraint size 3 because you got very different forcings going on. When constraint size 2, you have this nice thing that, you know, you assign a certain value to one guy. It says specific things about the neighbors. But when you got a hypergraph, you know, maybe these are 3 points joined by a hyperedge, it says something jointly about these two, which makes it a lot more complicated than saying, so if I set this to be 1, then maybe this has to, if this is 2, this better be 4, or something like that. It's a lot different than saying this has to be 2, or this can't be 5, or something like that. And that just makes things a lot more complicated for us. Okay, so, all right, so now I'm down to the part where I can start discussing proofs, but I've come very close to, well, I've used more than an hour time if we pretend I started at the right time, but I've come way too close to within an hour to give you all 3 proofs. Any preferences? Homomorphisms, that's Christian's request, I'll take it. Since he showed interest in the word at some point earlier in the talk. So, actually, I may not even get to that. It may more get to a review of the earlier questions because they're sort of necessary for the proof. So I said earlier results. We know k-colourability has a sharp threshold. We know this Estradi-Craignaud-Daudet theorem equals 2 sharp thresholds. So I'll start off saying why those have sharp thresholds, and then hopefully get a chance to explain how to extend the reasoning to our cases. So all those proofs sort of follow a similar structure. So suppose there is this unicyclic graph that boosts the probability of unsatisfiability. Let's say it's this one. Okay. So if we condition on this graph being present somewhere, that somehow boosts the probability of unsatisfiability. Okay. Well, we know that, suppose that we're in the realm where there are no unsatisfiable unicyclic graphs. Right? So we can assume this is satisfiable. So it's got at least one satisfying assignment. So let's say it's 1, 3, 2, 1, 2. So let's suppose that's a satisfying assignment. So I'm going to do something a little bit stronger. Instead of merely conditioning on this being present somewhere, what I'm going to do is I'm going to pick 5 vertices and say this vertex has to have value 1, this one has to have 3, this one has to have 2, this one has to have 1, this one has to have 2. Okay. And I'm going to ask, is there a satisfying assignment with those 5 variables forced into those 5 assignments? Okay. And clearly that's a harsher restriction than just the presence of H, since H is satisfiable. So if I can prove that even making those 5 assignments can't boost the probability by very much, that proves that having H can't boost the probability by very much. Okay. So this is a very standard approach that all these sharp threshold proofs using Friedgut theorem use. So the goal now is as follows. You've got a random, let's say in this case, graph. And I'm going to pick, let's say, 5 different random vertices. And say the first one has to have 1, the second one has to have 3, third one 2, fourth one 1, fifth one 2. And I'm going to ask, does making that additional restriction boost the probability now of unsatisfiability? Okay. And one's going to prove that it can't. Okay. Let's suppose we're looking at the 3-colorability case. Okay, well, in that case, we wouldn't do 1, 2, 2. We might do 3 there. So basically what happens now is you consider assigning the values one at a time. So I've got my random graph. I'll do them in this order. And let's say I'm up to fixing this one. So I've already picked someone, forced it to have value 1. I've already picked someone else, forced it to have value 3. And now I want to say, what's the probability of unsatisfiability given those 2 restrictions? Will I boost it with my 3rd restriction? So I want to consider them one at a time. If I've got any kind of symmetry, the first restriction is not going to change it. Okay? But after I've done a few, I might change it. So I want to show that it can't be the case in 3-colorability that adding one more restriction boosts things. And the way I do that is, well, the way Acleoptis and Friedgut did that anyway, is they say, well, what could it mean if I force a vertex to have value 2 for that to boost the probability of unsat? Well, let's say I pick someone, I say it has to have value 2, and now I'm going to look at its neighbors. And for it to have value 2, then I'm saying that each of its neighbors have the restriction 1 or 3. 1 or 3. 1 or 3. Okay. So the effect of forcing this guy to have value 2, the entire effect of forcing each of its neighbors to not have 2. And we want to claim that telling its neighbors to not have 2 can't be that big an effect. Okay. So to be simple, let's pretend it's only got 1 neighbor. And so I want to say if I pick a random vertex and tell that vertex it can't have 1 or, it must be either 1 or 3, could that boost the probability of uncolorability? Okay? And it's nice because that's a much weaker restriction. Telling someone you got to have 2, that's a pretty strong restriction. So maybe that might boost it. But telling someone it's got to be either 1 or 3, that's a weaker restriction. So it should be easier to show that that can't have much power. Well, suppose it does have a lot of power. Suppose it boosts by epsilon the probability of that you can't complete the coloring. Well, eliminate that. Don't make that restriction yet. And look at the graph, and look at all the 3 colorings in this graph, and identify a set of vertices that must have 2. Okay? So here's a set whereby every 3 coloring of this graph involves this vertex having color 2. All these vertices have color 2. Okay? And my claim is putting this additional restriction, pick a random vertex, has to be 1 or 3. That only affects things if you actually picked one in here. Right? Because that's going to change you from 3 colorable to not 3 colorable if you pick a vertex that had to have 2 and you make it 1 or 3. Okay? And so if this boosts things by epsilon, it means this set must have size epsilon n. Okay? And now here comes the sort of clever thing. If this set has size epsilon n, then I claim by just adding a few more random edges, I'll do as much damage as doing this 1 or 3 restriction. Okay? So suppose I added a small number of random edges, n to the 1/10 random edges. If I've got epsilon n vertices here, almost surely a few of those random edges are going to land in this set. Okay? And therefore, just adding an extra, say, n to the 1/10 random edges is going to bring me up to almost surely not 3 colorable. Okay? And if I kind of induct, that says that instead of conditioning on this h being here at all, if I'd added 5 times n to the 1/10 random edges, I would boost the probability of 3 colorability up to almost surely not. And then you kind of use some things, about phase transitions and so on, and you say there's no way with just a small number like n to the 1/10 you can boost it all the way up from anything sub almost surely all the way up to almost surely. You need a lot more than that. Well, I think not for less than root n. Right? I think that's one of Wilson's results, right? These phase transitions have to be at least root n.
What about if I take k-coarse? Is there just any 5 or something?
No, but that's coming from you're already close to almost surely and then up to the top. So what we're saying is suppose you're in a realm, that's a subtly different thing. It's suddenly appearing when you add a few edges. What I'm saying here is suppose you're in a realm where the number of edges gives you, say, a 50% or only a 90% chance of not being 3 colorable. Then by adding just a few more, you're not going to push yourself all the way over all the way up to almost surely.
Suppose the number of edges without That's the definition of threshold.
So when they first looked at that, they used the fact that for any property like this, it's at most root n. Okay? But later on, it becomes helpful with other problems to do like what Benny said, that in fact, if you assume you're coarse, then any little O(n) or even epsilon n for small enough epsilon, you can say shouldn't be able to boost all the way up to almost surely. Now that's not true for some sharp thresholds. For example, 2-sat, you got n to the 2/3 is sort of the scaling window. So adding n to the 2/3 can affect the probability of 2-sat dramatically. But that's a sharp threshold. If you're a coarse threshold, then you have to add an awful lot of edges to affect the probability. Okay? So that's basically the way this goes. And the key thing here is if you can get down to a restriction saying you can't have value 2, then this same argument works. So 1 or 3 meaning you can't have 2. This same argument works. So there's 2 sort of types of restrictions we can consider here. One of them is must be 2. Another one is can't be 2. It's easy to argue that can't be 2 isn't able to boost you up using this same argument. Okay? The must be 2 is a lot trickier to work with. In fact, that's the whole problem in a sense. All of these problems in general, you want to pick something and prove that it's got a sharp threshold, the whole problem comes down to saying that a bunch of restrictions like must be 2 can't do much. Now, for the domain size 2 case, which includes k-sat, here's why it works out. Because suppose you've got the restriction must be 1. That's the exact same as the restriction can't be 2. Okay? So when you got domain size 2, the one you really want to work with is exactly the same as the one you work with is exactly the same as the easy one to deal with. Okay? So domain size 2, that works nicely. K-colourability works nicely because the one you get induces the one you want on its neighbors. When I said we had this result about domain size 3, what really helped us is that essentially these are the only 2 possibilities. Okay? If you want to restrict on a vertex what subsets of 3 values it can have, okay? There's the trivial ones where you put no restriction, or where you forbid it from having any values. Those are easy to deal with. They're trivial in one direction or another. Then there's the kind where you say you have to have exactly one of the values. Then there's a kind where you have to have exactly two of them. Okay? And the latter is the easy one to deal with. The other one is one we start with, so it takes a bit of work to get from one to the other. But the fact that there's no other ones to worry about somehow helps us. Okay? Homomorphisms, well, actually, maybe, I mean, it's a little, yeah, okay. Suppose this is my graph. This is my target graph. Say 1, 2, 3, 4, 5. So this is my target graph. I want to get a homomorphism to this target graph. I'll do a similar thing. So I want to know if forcing a particular vertex to have a certain value can boost the probability of unsat. Remember, I might have already forced a few more. So my first thing I want to argue is that if any one value is such a booster, then all the values are such boosters. And that ends up helping us a lot. So suppose that, for example, forcing this guy to have value 1. Put another 2 up there. Suppose that's a booster. That boosts the probability of no homomorphism by some epsilon. Well, just like with the colorability, I'm going to examine what does that say about the neighbors. Well, in every neighbor it says something like, well, this one has to have 2 or 5. This one has to have 2 or 5. Okay? So that says that if I take a few vertices, it's neighbors, and in each of those neighbors I put the restriction, you have to have either 2 or 5, then 2 or 5 must boost the probability somehow. Okay? And now I'm going to put a even stronger restriction on each of them. I'm just going to say has to have 2. Okay? Well, if saying has to have 2 or 5 boosted the probability of unsat, then certainly saying has to have 2 is going to boost it, because that's a stronger restriction. So that tells me then that picking a few vertices and making them all have value 2 boosts things. And from that, one can argue that picking only one vertex and telling it has to have value 2 can boost things.
So you take a subgraph of the target graph. It's kind of like you're saying, right? Because you said 1 or 2 instead of...
No, it just takes the neighbors. Any of the neighbors.
I take a subset of the neighborhood.
But you take a subset.
And by repeating that, because the graph's connected, I can quickly say that for every vertex, the probability that it becomes a booster. Right? So vertex 4. Since 2 is a booster, 4 must be a booster, i.e. pick a random, make it 4. And then...
what if it's not connected?
Then we run into something awkward happens. So, I don't even have time. I'm going over time on this anyway, so I won't talk about the awkward thing. Yeah, for the theorem to holds for connected and loopless. So now let's look again at this fact that 2 or 5 is a booster. Okay, so if I pick a random variable and say you've got to be either 2 or 5, then I boost the probability of unsat. And that means, just like before, I've got these epsilon n vertices that can't be 2 or 5 in any homomorphism of what existed before I threw in that rule. And similarly, I've got epsilon vertices which can't be, if I focus on the fact that 2 is a booster, can't be 1, 3, or 4. Okay? And so on. For each of these 5 values, I got a set of vertices that can't take on a value from the neighborhood. And now if I throw down little o of n, like n to the some rational number, I don't know, 9/10 or something, I almost certainly get a star. And this, with high probability, in fact, I get a star that looks like this. And once I get a star that looks like this, then I'm unsat, because since it's adjacent to one of these guys, this one can't take value 1. Since it's adjacent here, it can't take value 2, and so on. And so adding this small number of edges, little over n edges, boosts my probability of brings me to almost surely unset. And then the rest of the argument just goes like k-colourability. So,
Which cannot take? This is the last argument.
okay. So this vertex, because it's adjacent to a set of vertices which are forced and not to be 2 or 5. No, what this is
Up there.
oh, what, this guy?
Yeah.
Oh, no, that's this is the one that's forced to be 2.
Oh, sorry.
Yeah, sorry. So I just picked some other vertex, some arbitrary vertex somewhere, and it's going to be adjacent to these guys. And because it's adjacent to someone here, it can't possibly take on value 1. Because all its neighbors had better be 2 or 5, and it's adjacent to someone who can't be 2 or 5. For similar reasons, it can't take on value 2, nor 3, nor 4, nor 5.
So it connects all the different triple.
Right.
So it can't do it.
Simple little argument. Well, I tried to do this a couple of years ago and couldn't manage, so it was either it was very foolish a couple of years ago, or I'm not sure, but it turned out to be a fairly short little argument to show that with homomorphism you get a sharp threshold. When it's disconnected, we get the problems that I can't, we can't argue everything's a forcer. When I move,
right? I mean, we know from studying homomorphisms that the loopless and connected.
yeah, but it might. I'm not sure if it's true or not. There's these funny examples I won't go into that may or may not be true. And what happens is, basically, it's something like this. Can I get a triangle-free graph so that the threshold for homomorphism to it is before the free colorability threshold? And if the answer is no, then all of these are going to be sharp. And I don't know what the answer should be.
Where does triangle freeness?
From the fact that this one is satisfied, that I can't find a small graph that all by itself is not homomorphic here. That I can't find a unicyclic graph that is not homomorphic to that.
And you can't do the mixture here, or the generalized.
Exactly.
Because
I
you
don't.
want to tell us exactly, you want to put constraints on that guy and be this
Right.
or that.
Exactly. I want to say exactly what the restriction on his neighbor is. And if I got mixed, I can't quite say that. When I go to hypergraph homomorphism, it gets a little trickier because I don't have a nice clean restriction on the neighbor. Just like I said before, I kind of got a restriction on the 2 other vertices that share that hyperedge. And that just makes it awkward. Digraphs we haven't been able to do yet. Maybe we can do that with trying a little bit harder. Not sure.
Should we conjecture for diagrams?
Well, let's close with a few problems. Digraph homomorphism. So the first problem is, what are the good problems? So as I said, at first I thought, okay, the obvious problem is characterize when you get sharp or not. But when we dig into it a bit, it's not so clear what the really good questions are. So here's a couple that spring out. Well, one is understand all of d equals 3 better. Either that or understand all of k equals 2 better. Somehow move out of that 2, 3 window that we can understand. And then the hypergraph and digraph. Now, I'm not sure. So the question is, for each of these, is it true that if your target graph is such that every unicyclic graph, every unicyclic digraph, for example, has a homomorphism to it, do you automatically get a sharp threshold? That's the case for undirected simple graphs. We actually have an example of a directed hypergraph where we think it might actually be a coarse threshold, but we haven't really, we came up with that, late last week. We haven't really been able to nail down whether it is or not. So it might be we have reason to think that by the time you generalize in both directions, suddenly it no longer holds.
What's the directed hypergraph?
So you've got hyperedges where there's an ordering on the edges. So say it's 3 uniform, the vertices are sort of ordered 1, 2, 3, or first, second, third. Okay? So it's naturally guess, if you go in both directions, you get the same theorem, but I think if you go both directions together, we might not have it anymore. So at what point does it break down? So, if there's a graph homomorphism problem, that's a very natural thing that has a coarse threshold, but every unicycle, I think that'd be very interesting, because that would be the most natural one to spring up yet, where coarse threshold without the obvious reason for having coarse threshold. Right, that would be. And in general, I guess what we want to do is look at reasonable subclasses. So a slightly less broad generalization of SAT, or CSP, under which we can prove things, characterizing whether there's a sharp threshold or not. Ones that avoid the really contrived, nasty things like that one I showed at first, where you needed to know the 3-colorability threshold. That one obviously can get plugged in because the family's too broad. And there's certainly room to have a broad family that doesn't include that one, and yet it's still interesting and worth looking at. So, like I say, this is fairly early in our study of this, but this seemed like the sort of problem that people here might be quite helpful at. So, if you're interested, let me know. We'll think about it for the next week and a half.